So I'm loading in, running a little behind schedule, but we're here, making steps. And we're here at the end, at least for the schedule of the course. Today's really like first day working on project number 3, looking at just a little rocket science. Should be easy, right? But it's the same kind of problems that we've been working on, where we set up a differential equation and then we're trying different ways of integrating it, and then to tie it all together, is that now we can use those root finding methods to actually like optimize kind of problems. So you have a numerical problem where we can enter parameters in, and then we know what happens, and then we can invert the problem, or we do some inverse problem solving. If I don't know what mass rate I want to burn the rocket fuel at, I can just try one and keep trying until I get the right answer. It's like the general goal here. Anything come up so far for like either project or kind of concepts about module 3?
Yeah. So the first part of the project, we can get into the simple rocket function.
Yeah.
Obviously, we're supposed to put in kind of our work to figure out the derivatives for the new function to get the derivatives.
Okay. Yep.
But unlike previous ones, you already have something in there that's you basically created a blank array, or array full of zeros, which hadn't been done in previous types of these solutions.
Okay.
I'm curious why that's the case here versus before, because usually we just calculate, derivs equals.
Oh, I see. Like y setup.
Yes, why is that there? Because when we just normally, in this case, at least the documentation says we're going to just spit out derivs instead of d state.
Yeah. So let me make sure, because sometimes I have, I guess the only real reason for that is that like if you try to integrate this equation, it'll work. It's always going to give you zeros. Like at least derivatives are always 0. And it's the right shape for that input of state. And what we had been doing is that we were always dealing with a state with 2 things in it, a position and a velocity, or something like that. And here we just have position, velocity, and mass as to describe like what is the current state of this rocket. So yeah, it's not.
Is it wrong to do what we did in previous ones?
No,
no. You can even call it d state, but d state equals, and then you put in the derivatives of each.
Yeah, like you could plug in the derivatives right into an array right there.
Okay, so that wouldn't affect the solution.
No, it's just as it gets longer, sometimes it makes sense to say like, all right, my d state of 0 is state 0, or sorry, state 1. My bad. So doing it line by line, so we can say dx dt equals v, or even have like an extra step of.
I see what you mean. So it's just splitting it.
Yeah.
Okay, so if there's 7, 8 variables in your state function, it just makes this cleaner to look at.
Yeah. So your lines aren't stretching longer.
That's all it is. Just the syntax.
Yeah.
Okay.
Yeah, and sometimes it helps to use the actual shape of your input to match the shape of your output, especially for stuff like this where you're integrating, where you need the shapes to match up really well as you're sending them through for loops and
What
other
is the
functions.
shape in this case?
Oh,
Or the first one, or I guess the original state function for state array.
so if our so we're starting off at 0 height, 0 velocity, and 1/4 of a kilogram. Oh. I'm hitting too many buttons at the same time. So in this case, it's so for NumPy, we can have as many dimensions as we want. In this case, we have 1 dimension with 3 values in it. And some
would it not match that shape anyway if we just didn't put in that destating nv.shape?
Yeah,
Okay.
yeah. Like if you want to match to MATLAB kind of syntax, you can put 2 brackets in there, and now it's
1 row, 3 columns.
1 row, 3 columns. But yeah, that's true. I say that it's derivs, but really in here it should be dstate, right? Because it's not returning that. It's a dummy variable anyway. Like it doesn't actually get used, but better to be consistent. It's matching, undoing whatever work I had been playing around with online.
You starting to get sick of that too? Yeah. I know, we've been trying to problem solve. You know, we've been doing that.
Yeah, no, I was thinking that. Yeah, what could we do with that? I've never seen the preview before. But I think you just posted stuff.
So keep posting them.
Yeah.
Yeah, I don't know. He's just like, you're using these equations. Now we're using them, so I guess we need to do whatever the exam is. One of the easiest ones I think I've ever taken.
Yeah, I told him, like, you know, like, we need to. Yeah. It was like, you were even like a little thing. No sense. I don't know. Yeah, usually it's easy to fix this get, especially stuff server error. Yeah, yeah, you can 9 times out of 10 it's just not blocked out. Yeah, block back in. Yeah, because it's not like computer hardware stuff. It's all cloud. Yeah. So yeah, internet resulting sooner or later works. Yeah. Okay. Thanks. So if you look at, I mean, yeah, it says here, and then there's like the actual differential equation. That is our. It says order of operations. It's E over M times B.
So we're going to be some good computational scientists here. We're going to go through a couple of, like a 3-step process. Step number 1 is verify that if we integrate this equation, we can replicate a math equation that is like something that we don't have to derive it, but someone derived it. It's not hard to derive, but so in this case, here I'll move up a little bit. If I'm trying to solve equation 1, and my biggest factor is just that u times dm dt, like that, it's much bigger than gravity, much bigger than drag, which is the case like if you're in space or if you're just beginning to take off. So it is, and it's also if you have like a lot of thrust, then that is the equation. Then it turns into this like equation 2a, and 2b is the solution to that. Is the ratio of your current mass to your initial mass is like the e to the change in your velocity. So there's like a log proportion of like how much mass you expel versus how fast you're moving. It kind of breaks down whenever you expel all of your mass. Like if you are moving at 100 meters per second and then you become 0 mass, technically you're moving an infinite speed, but you're not you anymore. I don't know, because even it's kind of tough to get rid of all of your mass in a payload, but we have an equation. Technically it works even for 0 mass.
Wait, what is the last term?
Sorry?
For equation 1, what is the last term?
Oh, CV squared. Oh, so we have yeah, let's come up. Our main driving force is the fact that we're expelling mass. So that's like our loss in mass times u, however fast it moves. That's like our thrust. And then force of drag is some constant times v squared. And then gravity, we're trying to go up off of the earth, so gravity is also opposing. All right, so all of that is to say, simple rocket, when we're thinking about like, all right, because some people were kind of taking this and saying like, all right, well, let me grab that since it's in the documentation, and Professor Cooper is big on documentation. When I take these terms, I'm trying to solve for the case when gravity is negligible and drag is negligible. So that means G equals 0 and C equals 0 for those terms, because we're trying to figure out like what is the total effect there. What about what's the change in mass at every time step? Like if I have 1/4 kilogram, I'm burning at 50 grams per second. So how many kilograms do I have left after 1 second? Or 0.1 seconds, something. Like what's my change, what's the dm dt for the last one? Current mass, let's say it's 1 kilogram. Start at 1 kilogram, and I'm burning 50 grams per second. What do I have after that? After 1 second.
950 grams.
Yeah, so it's got to be minus. So whatever my mass burn, I have a positive thrust because the more mass I throw out, the faster I'm moving. So it's positive, pushing me up, but then my change in my mass is a negative dm dt. Otherwise, you have like a vacuum cleaner somehow. You're like propelling yourself by like sucking in mass at, which would be kind of impressive to see, but I don't know if it would work. It seems like something from Spaceballs. How are you is anyone trying to integrate this yet? Yeah. What were you using?
Start with Euler step.
Euler step? Yeah, Euler works. Any other? We had a few different integration methods from the reading. Have you seen like the SciPy solve IVP yet? This one, it's a great, so we went through and looked at kind of like in depth, like what are the mechanics of integration methods, and for the most part they were all the same. Like there's a difference between explicit and implicit, but everything else is just something like you calculate a derivative, multiply by a time step. You can do that 4 times, you could do it 20 times, but somehow that's getting you to the next step, like somehow. And solve IVP is a nice like wrapper for lots of different integration methods. And normally if you're solving IVP is initial value problem. So we have initial values. We want to predict future values. Then the default method is a Runge-Kutta 4-5, which is similar to Euler method, but instead of just one, or that Euler-Kromer method where we use like 2 derivatives. We had like the step and half step derivative. 4-5 is now using like 4 half steps to calculate that, but it's still a nice like explicit method. And we can even scroll down to this method description and see that by default we get a 4-5 Runge-Kutta explicit. There's a 2-3 method, another Runge-Kutta order 8, so that one's using 7th order, probably like 7 data points along the way. And then there's even a couple of like implicit methods that we could play around with just to see if there's any difference between explicit, implicit. For this one, I mean, it's a rocket taking off. It's not like oscillating or anything, so we're probably not going to see a big difference between implicit, explicit. At least I wouldn't expect one based on what we've seen so far. So I could try this if I want to. Oh yeah, but I should check out how to actually use it. Yeah, let's try that. So I'm just copying in like the first few things and see if I can match those inputs. What would the function be? What would that one look like? What function am I trying to integrate?
2b is. So that's final mass over the initial mass equals e to the negative delta b over u.
Oh, that would actually be the solution that we're trying to I think 2b, that is a solution to the problem that we're trying to solve. And this is our first step, is a verification step, is that we can create that function. So if I can do that, then I can start adding drag and gravity, and I know that at least, even if other things go wrong, I know that my process of like integrating a function and solving a derivative, solving like a differential equation, that's all working correctly. This is a good process, like especially for senior design when you're working on something. That's why you start off with like a unit problem that is, it's not always like easy to solve. It doesn't make it easier, but there is a solution, so you know that you're converging to something that is real, like that at least like predictable. You know that it's predictable, and then you can start adding other stuff. Like, yeah. So our function is that like simple rocket, right? So given these initial values of 0, 0.25, I want to figure out what the rest, how high it goes, how fast it's moving, and how much mass it has left. How long is the time span? We'll start at 0. How long can we burn before?
Right below. Initial mass minus final mass.
Yeah.
Over
Yeah.
your mass change rate.
Yeah, I guess I could grab this, right? So I could say like t -1 like that. Then my initial state is going to be that 1/4 kilogram, 0 height, 0 velocity. I can leave it as this default Runge-Kutta 4-5 method. And then, yeah, I'll try that. And right now I'm just running it, like I'm not saving anything, so it's just going to print all the outputs. At least it should print all the outputs. But instead we get okay, nice. It's telling me that it can't unpack a float object. What does that mean to you? So here,
Trying to step through a float, and it should be an integer.
yeah, so this one, like this state, it's plugging in, because state was an input for my function. So I gave it a value of state, but that value is a floating point number. So right now, you could think of it like state is the number 1.325 or 0. Like maybe it's just the number 0.0. And that's most likely what happened because it failed on the first time step. So it's trying to unpack a floating point number, but I can't do that. I can't say that HVM equals 0. Actually, yeah. So I'm reproducing the same problem. Now it's telling me that it's an integer, but it's like, well, what the heck, solve IVP? You were supposed to make my life easier, but you're just making things harder. All right, the very first thing that it tells us is that the function is a function of time and state, t comma y. And this is like the general form of differential equations, is because sometimes you have forcing functions that are a function of time. Even this like mass, we could say that m is a function of time rather than leave it as part of our state. No, it wouldn't make much of a difference, but so there's two things that I could do. I could either add a t right in here, or I could use like lambda, like make an anonymous function, and then force it into that t comma y output. Oh, I don't need that one. And it gives me all this stuff. Oh, yeah. So it gives me all this stuff. NFEV is like number of functions evaluated, like how many times it ran through that simple rocket equation. Success means that yes, it reached the end of that time period, like it didn't have to stop because it hit some kind of not a number or something. And then time and y, like t and y are the actual solutions for when things were solved, like at what points did we get solutions, and then y is the actual state values that we got there. So I could say SOL is that. And if I want to look at just the height, I should probably have we didn't get like a lot of solution. Oh, sorry, go ahead.
What did you do to fix the error? Not everyone group?
What I did was I changed this input to get rid of, so that it gives the solve IVP a place to put time, even if time doesn't get used in my function, but it's always like time and state. So it was trying to use the time, but that's what was plugging in for my state. So we can see like these integration methods, they have different time steps, and those kind of optimize, like they're trying to optimize the number of times you have to evaluate the function. I don't really care, I just want a better curve so I can change like my function evaluations, like t eval, make that equal to like 50 steps. So I get like a smoother kind of constant time step solution. So if you want to try something new, solve IVP is more of like the industry standard that if you have an initial value problem, most people would use like a built-in function to solve it. Again, if you're working on like a microcontroller for a battery and you have only so much like RAM and disk space, then yeah, maybe hard code in your own like Euler or Euler-Kromer step. But if you can't, if you can import a solution, solve IVP works.
Yeah. So I was able to integrate the numerical solution. Now I want to compare it to the analytical one.
Okay.
And I want to graph the analytical one.
Yeah.
And I'm having trouble with that because if I just take the initial function here, these are all constant values except for delta V. So this could have, this would be your final step basically. This equation represents that because you know your final mass, you would know at the very end.
But you can also think of it as the final mass from time 0 to.
So can I use essentially
current
the
mass
for the analytical solution to step through masses basically that match the same thing as they'll do the same steps along the way as the numerical solution, correct?
Yeah, exactly.
Okay. So basically I solve for delta V because our initial velocity is 0. So it's just V final or whatever V at that state is. And then I can plot like I did down here. This is velocity versus
mass ratio.
Okay. So I can do the same thing, correct?
Yeah.
And then in theory the difference is the error.
Yeah, then that difference is an actual numerical error. And because you use an integration method, you introduce something in comparison.
Is P.1 is that base E?
E.
Okay. So we have the initial velocity. This is something bounded backwards. So the initial velocity is 0.
This one is velocity versus mass.
Yeah. This would be the same thing. It's starting at
But it's
0.
and solve. Like if you're taking log and solving. So that would be V versus V. V versus V over M.
This is mass. The second.
Okay.
So in theory, that's your mass. As
Yeah.
it's stepping through each one.
So using the same
Because that would make sense using the same values because it's stepping at the same rate the whole time. If the analytical solution, because I mean, if you're solving for delta V, you take the log of this, multiply by negative mu, and you get delta V.
Yeah.
But the problem I think here is we're getting the first step. It's like it's going the wrong direction. The first step is going to be M0. Over M0.
Well, this one is a fixed function for a given m. For a given m, it's always an output of delta v. So whether you go forward or backward, or you inside out, it's always going to give the same answer.
It does.
Or wait, where's the numerical solution? So numerical says it's good. Is it just on top of itself?
There should be an extra line on the bottom of the line. So that's the numerical solution, which makes sense. You're seeing your velocity.
Yeah.
As you're
Now
you're reaching
comment what you just did.
You're reaching max velocity.
I think they're on top of each other.
But then what's this?
Oh, because you started at 1. Or you went to n minus 1. You can just get rid of the loop and just
Oh, the whoops, I see what you're saying, yeah.
just undo that.
You just go ahead and
Yeah, go ahead.
start at 0.
And I think they're directly on top of each other.
Sounds good.
If you add a marker to your resolution, that helps highlight. Yeah.
So is that correct? I mean, they're on top of each other. That means they match.
That's a pretty good match, right?
Okay.
Yeah.
But that's the way to do it, essentially. Is you do your numerical integration, and then you can plot it against this.
Yep.
And I can even, like, is it worth even calculating the error?
You can, like, if you want to dive into, like, how much is this, like, how much am I losing by numerical methods versus.
But this proves here that
But they're, like,
this
if
is,
you can't see the difference on,
Yeah.
on a plot like that, then you probably can't even measure it.
Okay.
You probably were like, yeah, use correlation to drive it around.
Cool.
Yeah, so that was the problem. We just couldn't see the.
Yeah, there's one extra, yeah. Good problem.
Yeah. Anything cool happen? Yeah? What happened? Nice. A graph? Alright, so we were just playing around with so we can use solve IVP, we can use Euler step, we can use all these different integration methods, but the goal is like, how do I show that it is this equation, that 2b is not 2b, that I have that solution. So this is showing that relative mass, like your current mass divided by your initial mass, is always some like e to the v. So like the log of your mass is your change in velocity. So to start off, like I would just, let's put let's just see what this thing looks like. If I could spell. So this is mass on the so if I just look at like how fast am I going versus how much mass do I have, here the x-axis is kind of backwards, right? Because we start at a 1/4 kilogram and we keep burning, so the more we burn, the faster we go. So the final speed is like 400 meters per second. Oh, and we're out of time. Oh, sorry, cliffhangers. And it kind of looks like, so I guess here, if I squint and look at it, it's like, oh, that could be a log problem. So the next step is like plotting that log of the mass. See if we can get it to match this one. Then, but first we got to enjoy the weekend. It's time to go. All right, thanks a lot.
I think that's correct.